Good morning, everyone, and welcome to the fourth session of the Quantum Technology for Policymakers training. Today, we will talk about quantum metrology. And before we start, I'd like to present you the team and a little bit about you and a little bit about the training that we are having. Together with me, my name is Oxana Mishina. I'm working at the CNR in National Institute of Optics in Italy, in Trieste in particular. There is Costanza Toninelli, Professor Costanza Toninelli. She's an experimental physicist in Florence, also CNR. And Diana Tartaglia, I'm sorry. And she's doing a PhD in quantum technologies and focused on the impact of communication about quantum technologies in our society. And I would also like to thank a lot all the QTZ Flagships, Quantum Flagships Coordination and Support Action Team that is providing us with a lot of useful information and supporting preparation of this training. The main goal that we try to follow in accordance with what we have designed together with the European Commission, who actually did a request for this training, we would like you to gain the knowledge to take informed decisions and cooperate with peers from other countries and sustain a conversation with your fellow physicists and experts in the topic who are now even closer to you. And for today's training, we've had 51 registration, and we analyzed a little bit your stats, and we see that we have 19 countries covered, and we have more and more balance in covering the countries of people registered. And 37 of you, which is a huge percentage, more than 75, are the people who keep themselves informed in quantum technologies and are really on the edge. Some of you still want to know more because they feel like they don't know much, but I'm sure those are the people who know even more than all of us here. And only 1% feels to say that it's only marginally that the knowledge this person has about quantum technology. So this is about you for today. And I would like to start presenting our speakers. It is my pleasure to introduce you Dr. Davide Calonico. And his biography is long, and I'm sure you all read it on the website, but just 5 key points that GPT chat helped me to pull out of his biography are the fact that he is working currently in the National Institute for Metrological Research, INRIM, in Italy, and that he dedicated a lot of effort for the precision measurement and metrology over several decades. And at the moment, he's a leading expert in optical clocks and frequency standards, and obviously recognized beyond the INRIM Italy and worldwide. And last but not least, he's very committed to pass and to teach the scientific knowledge and metrology to the next generation of researchers, which is not to underestimate. So please, Davide, I stop sharing my screen and welcome you on stage. You're muted currently, but let's ask Tom.
Thank you very much for this nice introduction, and good morning, everybody. I would like first to thank QTZ and the Institute of Optics of the CNR for this opportunity to talk about quantum metrology. And so I'm going to share my video and to put it full screen. I hope to share the video full screen. Okay, so in this moment the video is full screen, and I will talk in the next 15 minutes about the basics of the primary metrologies and quantum technologies, with some focus on 2 particular platforms, in order to have some take-home messages that could be quite clear, and I hope also of the highest interest for our auditors today. And First of all, I would like to stress the fact that in Europe, we have a coordination about the metrological institutes concerned or active on quantum technologies, and this coordination is called European Metrology Network on Quantum Technologies, it is an initiative of the Euramet, that is the European Metrological Association, and many of NMIs, so National Metrological Institute, like INRIM in Italy and in other countries, are part of this. And the idea is to provide a reference for different communities with respect to metrologies in this particular research topic. So quantum metrology is also linked to all the main pillars of quantum technologies at large, like metrology and sensing, communication, computing, and in general to enable the technology both for research and for companies, for European industry. So three platforms are a bit more interesting for this network. So we have quantum clocks, quantum electronics, and quantum photonics. Today, I'm going to talk a bit more on clocks and some take-home messages about photonics. Of course, I will not be exhaustive on these two areas, but I've been requested to have some use cases and some examples, and this is the goal today for myself. First, so quantum metrology, the shortest possible history. So since the 1967, time is quantum. So the atomic clock definition, the atomic time definition for the unit of the second in the international system is from the 67. But in the decade starting on the 70s, also electrical standards went quantum. And going quantum is not something that is freeze forever. Of course, the evolution in this quantum primary metrology has offered the possibility to embed more complex phenomena and other aspects of quantum laws. And in the 90s until the 20s, for example, atomic laser cooling and quantum optics makes a quantum leap in accuracy for this area. And also nanotechnology is opening a new frontier. Today, we are really focusing to use the best of quantum physics and quantum technologies like nanophotonics, to use the entanglement to put atoms on a chip, and to have nanostructures and new materials to be exactly on the quantum metrology edge. That is one of the goals of metrological institute like INRIM. So focusing a bit on clocks. So the main point here in our community is the change, the evolution from microwave standards to optical standards. So from standards that are using references in the microwave frequency domain to optical domain. And this is because we have a better performance in accuracy than a Cesium microwave standard. And this is obtained, of course, by intrinsic natural law together with a lot of technological tools. Here for the optical clocks, optical atomic clocks, of course, laser cooling, atomic state interferometry, laser clock reference, squeezing, and entanglement are the keywords for the present status of the art and the evolution that we are looking at. So these are 5 quantum physics keywords that are very, very relevant for timekeeping presently with the atomic time. So a few slides just to show pictures. This is, for example, a microwave standard and cesium fountain that is the best realization of the second international system today. And as you can see, this is the fountain at INRIM. one of the 10 patents around the world, keeping the International Atomic Time at a good pace, let's say. And when we move towards optical, a lot of visible lasers stepped in. And this is a picture of the ytterbium laser cool optical clock at INRIM. Ytterbium is one of the possibilities. It's not the only atom that is making a big difference in the time and frequency community. This is another one based on strontium atoms, again present at INRIM. And of course, this change towards optical has offered the possibility to improve of a factor 100 to 1000 the accuracy of these devices. Ions are also very good candidates for being clocks, like ion clocks. This is a picture of an experimental apparatus at INRIM that is based on barium ions, and on the right you can see a Coulomb crystal, a so-called Coulomb crystal. I would like to stress the fact that neutral atoms and ions are suitable for clocks and for quantum computation. So the basic pillars, the technology is exactly the same. Of course, the verticalization, the specialization is different with different issues and challenges, but we start from the same physical and quantum technology. Who needs an optical clock? So the redefinition of the international system of units is ongoing. So we are considering to move from cesium to optical transitions with the different atoms. But clocks are very important also for testing fundamental physics, to empower techniques like radio astronomy, and in particular in space are very relevant to navigation, this space exploration. And last but not the least, in recent years, thanks to the optical clocks, we can have also accurate geodesy, in particular relativistic geodesy, exploiting the gravitational redshift, it's called gravitational redshift on clocks. But today, I would like also to show you that one of the important trends in this community is to miniaturize and to arrive, for example, to having an optical clock on a chip. So today we start from bulky clocks at the highest accuracy. We would like to move to compact clocks and then to micro clocks. In this moment, transportable clocks are reality. You can see in the slide a transportable clock made by PTV in Europe, so the German institute. But we have another, for example, very, very famous transportable clocks in Japan, and others will come. At INRIM, we are starting to build up a transportable clock. And in the slide, you can see a compact microwave clock made also in strong relationship and collaboration with companies like the Leonardo company, to offer a compact solution, but yet a high performance, for example, for navigation and the clocks on the Galileo system. The next step is to move to chip scale. And here you can see some of the realizations so far. The quest for having high performance chip scale clocks is just very recent, let's say 5 years at the largest possible time window. And there are increasing possibilities and increasing achievements, just to get what is quite obvious, that a reduced weight, volume, and power, and easier operation will make a leap in science and technologies, will bring metrology on a chip, will have other quantum applications, but of course will be exploited by satellites that are always more and more reduced in size and volume. And for example, here, just as an inspiring image, I reported that the deep space exploration and the Moon to Mars project of NASA And in the upper case, we have satellites and, for example, the reality of the Galileo system in Europe. Of course, the deep space exploration is as well very important for the European Space Agency, the companies and the research groups that are working on this incredible challenge. So we pushed accuracy a lot during the last decades, and we were a bit limited by the system to spread our uncertainty. So you can see here that, for example, optical clocks are limited by using only satellites to spread the accuracy of the clocks. But then we have started to use optical fibers to offer the accuracy of the clock in the lab to any user. And this works. And this is very relevant today also because we started this use of optical fibers, building comparison among atomic clocks. And now we are going towards a pan-European network for time and frequency and quantum. You can see here several publications, but you can see that there are a lot of applications and also quantum communication. Potential strong synergy between quantum metrology, sensing, and communication, and involving not only the metrological community of Europe, but also Euromed and EuroQCI, for example. This is an example, a use case that I would like to show you today. What is EuroQCI? Is the European Quantum Communication Infrastructure Initiative started in 2019. So a plan to ensure ultra-secure communication using physical quantum communication. And we have a terrestrial segment based on fibers and also a spatial space segment that is managed by the European Space Agency. And this is part of the big frame of secure space connectivity initiative. So, for example, in Italy, we have built an infrastructure to spread the time distribution of WellBI geodesy. And now we have that this infrastructure is serving the Italian implementation of EuroQCI. And in particular, the project QUID is aiming to have quantum metropolitan area networks federated and also connected by this backbone with long-range QKD, also maintaining time and frequency distribution. And for example, frequency metrology can help QKD in long range, like in this protocol that is a twin field QKD, where solutions derived by atomic clocks comparison, ultra-stable laser, active cancellation of the noise on the fiber has been used to provide a new protocol in quantum key distribution. The contribution of frequency metrology to the photonic, the single photon platforms is not only this one. So I would like to stress also another part of our core business, that is certification and standardization. So National Metrological Institute are very well active in standardization bodies for quantum communication like ETSI, CENELEC, and this is also within a research project at the Euromed level. But also we are building testing facilities for QKD that have the objective to test, characterize, having a benchmark of components, but also testing and having a certification for physical security implementation. So this is a big challenge, but really in synergy with the European quantum communication infrastructure can make really these quantum technologies progressing in a very significant way in Europe, of course, and also at the global level. So in conclusions, my take-home messages is that the European Metrology Network for Quantum Technologies is a bit of the core of our contribution to European quantum technologies, that we are using platform based on atoms, electrons, photons, that today we have a bit focused on clocks and their achievements and the next steps concerning miniaturization. Using fiber networks for clocks, we are moved towards quantum communication, and so we are putting together metrology, sensing, and communication at the European and global level. And metrology for QKD has different aspects, and they are all relevant, and the community is really looking to offer to the correct impact and to respond to the needs of the European citizens and society. And INRIM is doing all the efforts to be an active part of this contribution to the evolution of Europe and the European Union. Thank you very much for your attention.
Thank you very much, Davide, for this very, very intense and super interesting presentation. So now we are halfway through, and I would like to invite our next speaker for today. And let me introduce him beforehand. So our next speaker for today will be Nicolas Spethmann from the PTB, which was already mentioned today by Davide. And the GPT chat, 5 key points from Nicolas Bio are telling us that he did his PhD in quantum technology with single neutral atoms in Bonn in 2012. And he was a Marie Curie fellow and constructed the quantum limit atomic gases, cold atom gases at the quantum limit at the University of California in Berkeley. And then he joined the Physikalische Technische Bundesamt PTB and worked on quantum logic spectroscopy. So from 2020 to 23, he served as the vice chair of the CERN's CINELECT focus group on quantum technology. And currently he leads the Quantum Technology Center QTZ at PTB in Germany. So please welcome Nicolas, and we are looking forward to hear your presentation.
I'm happy to be here. First of all, thanks for the very nice introduction. And I'll try to connect to what Davide told you already. I think it's not a big deal that we do it the other way around. So maybe just a few words and make a connection to quantum technology. So I'm from Physikalische Technische Bundesanstalt. And of course, one of our main tasks is the realization, dissemination of the physical units. And since 2019, we have a big change here, because now we don't have artifacts anymore, but rather a definition of the natural constants without uncertainty by law, basically. So that means you can now take, if you want to realize a unit, you take the corresponding natural constants, as you see here on the left, and then you build a device that's deriving your unit out of it, which is, of course, in most cases using quantum physics. And also in that sense, metrology institutes are dealing a lot with quantum technology. Let me briefly check. Do you see now my second slide?
Yes.
Okay, perfect. So on this slide, I just want to briefly mention this connection between quantum technology and metrology. And of course, Davide already made this connection, but maybe also to focus on the new SI. So if you now think about realization of the second, of course, we deal with clocks and frequency dissemination, but also strongly related ion trapping. That's relevant for quantum computing, for instance. And the same is true for electrical quantum metrology. Realization, dissemination of the volt, strongly relevant technology is used for superconducting quantum computing architectures. And the same if you look at radiometry or single photon science, we have a strong connection to quantum communication, and we already heard examples about this. And my point here is that national metrology institutes and metrology in general, in that sense, has a strong connection in terms of characterizing and understanding components in all the domains of quantum technology. And this is also what I would like to tell you about in the next 10 minutes or so. I will try to give you a few points, at least, about, from our perspective, metrology in Europe and also novel opportunities in quantum that is also strongly connected to the new SI. So I think one thing, if you look into, if you compare Europe to also other countries, we can say that we have a very strong and established collaboration and networks in Europe dealing with characterization of the devices in metrology, as for instance EM&Q, and also projects like QTZ, and of course many more. Another point that's very strong that has been mentioned also already and is furthermore connected to characterization is a strong role in standardization, and just mention one example here. And I think overall we can say that we have a competitive and strong quantum metrology in Europe that is also characterized by strong collaboration with academia, but also with industry and technology transfer. And this is what I want to show you, just 3 examples in the next few minutes. And I will try to focus on 2 points that from my point of view are very important for quantum metrology and quantum technology in general. And one point is to now exploit quantum metrology, the newest AI, for novel applications. I'll give you some examples. And then also think about quality infrastructure, creating trust and reliable measurement, independent characterization in components that we need to build this new quantum technology ecosystem. Okay, with that, I'll come back to that slide. With that, I would like to jump into a few examples. And as Davide said before, this won't be exhaustive and it will only touch upon those topics. Still, I think it's very useful to look at those. So one example I brought today is a robust optical clock. So this is a demonstrator of a turnkey so-called optical clock. And the idea basically was of this consortium of industry and academia and metrology people to basically take what's in the laboratory into something that is turnkey, robust, and also transportable as a frequency standard. So this is a device that's now being, by one of the industry partners, being developed as a industrial prototype. And I would like to compare this, now that it's going into actual application, also used by industry, to what's around there. And one comparison you can come up with is with a commercially available microwave maser here. So you see the key figures here. So maybe it's sufficient to say at this point that this is based on an optical transition and this one on a microwave transition. So there's a certain advantage that you can see here. Because you have a higher frequency of your reference, you basically can get better properties that are elaborated here. So in the end, you get a better frequency standard. I also would like to mention that this device also, and this is in the spirit of what I said before, provides an absolute accuracy because it is referenced to, in this case, an atomic transition. So this basically is just a point of comparison where we can see there is a competitive device coming out of the development, and industry is starting to use this as prototypes. You can also make another connection that is, if you look at chip scale clocks that, for instance, were developed in the United States by our colleagues at NIST, but also by companies. I don't want to go into detail here. I would say that this is a somewhat complementary technology and is addressing a slightly different market, but I would also say that also here we can see that this nicely fits into this existing things that are happening, and we can provide novel opportunities here in Europe. Let me switch gears a bit. So this is example number 2, and this is now something different. This is about pressure sensing using quantum technology. So on the left-hand side, you can see the traditional way of doing this. In the end, you measure a force per area. This gives you a pressure using, scales, basically. With the new SI now, what you can do is, instead, you can measure optical path lengths in an optical resonator, as seen here. And because of the new SI, without going into any details, this again gives you a measure of the gas in this device, a measure of the pressure of the gas in this device that can be self-calibrated in some sense. And again, this can be very useful for certain applications, because if you want to measure a pressure, say in a process in a large factory dealing with chemicals or something, it might be very important that you actually understand, without a calibration, the actual absolute value of your pressure measurement. And this is shown here. So this is what's meant here with automated and faster calibrations, that you get also lower uncertainty, minimized dimensions, and so on and so forth. And I would like to stress that this was a project that was conducted with different partners all over Europe. And there's now a follow-up project that's shown here. And again, we have people from metrology universities, but also from industry to early on look into this technology. And this is now building on the previous results. This is actually taking off now for the next stage. And in the end, the goal is really to have like a, in this case, quantum-based measurement of the pressure that can be used also by end users. Okay, and finally, the last example I will make is about electrical quantum metrology. So here you see a picture of the device. So it's based on superconductivity, and it's about voltages. So you can have creation and measurement of voltages here. So what you do is basically you use a certain superconducting device. It's shown down here how it looks in real life. And then if you do this right without going into any details, again, you can have a voltage that only depends within certain limits on natural constants. And again, this gives you something like a primary quantum voltage within USI. So you can have a device that gives you a measurement or a voltage that doesn't need to be calibrated or can be self-calibrated. Also, it's a very precise device, as you can see here. The accuracy is given here, and the scale can actually be volts, can be DC, can also be arbitrary wave. So this is like, from my point of view, a very universal tool for future applications coming out of metrology. Again, the question is there a market? Is what's happening here in Europe and otherwise? I just brought, again, a few examples. There's a company in Germany that offers commercial versions of those devices. You can buy them. We also have companies from the United States, and actually NIST is also offering those devices. So this is already on the market and starting to be used. Okay, with that, I would actually like to come back to this slide. So I hope I showed you just a very few examples how we can use quantum metrology, and I focused a bit on this on the new SI. I would like to make a few points about characterization, independent measurements, and quality infrastructure for quantum. And I just brought two examples here. And so one is about ion trapping that can also be used, as we know, for quantum computing. And what we set up here in this, shown in this picture at PTB, is a unified device, that apparatus that allows unified test procedures for characterization of ion traps as a service for industry partners. And the same is also happening, just as an example here, on fiber links that we operate for quantum communication components. And in those cases, we already do test devices in cooperation with industry. And this is also what Davide mentioned, a service that we try to set up to create trust, independent measurement, and reliable components for quantum technology. Yeah, with that, I would actually just very briefly mention opportunities for further reading. So there's a comment in Nature Physics from several NMIs and National Metrology Institutes that expands on those ideas. There's also an overview article about standardization, including characterization of components, as shown here. And this has already been mentioned by Davide. I also think that the European Metrology Network is really a key activity here to offer services in Europe for the upcoming industry. And also QTest is instrumental to actually expand on the testbed idea for industry and support of quantum technology. And with that, I would actually stop where I started at this slide, and I'm hoping for questions and a discussion at this point. Thank you very much.
Many thanks, Nicolas, for this very, very great overview and nice presentation. And yeah, we have now a really comfortable quarter of an hour for questions and answers. It is great. And I welcome all the participants to either write them in the question and answer section Or you could also just raise your hand and then I will open the mic and you could simply speak. So please don't feel shy and come over with questions. And in the meantime, I will ask both Davide and Nicolas to just reflect, as this is my personal curiosity. So like the standards, they have started them a long time ago to have standards, maybe not that long time ago to have international standards. And from your point of view, how frequent, how often they change, and what are the dramatic changes in standards, and where would you localize this change towards quantum, the use of quantum technology in the standards?
Well, Davide, if you like, I can start and then you add to it. Okay, so I would say, so we did work on the needs for standardization with the community in the focus group for quite a few years to identify what is the need in standardization, of course, not from the perspective of national metrology institutes alone, but the voice of industry is, of course, the most important point here. So if I understand your question correctly, you're asking about the timing of standardization, also about the international dimension. So about the timing, we do have in the roadmap that I referenced in my talk, we do have an estimation of what the timing would needs to be from this consensus out of the focus group. I can give you a few examples. For instance, if we now set up testing facilities, as we do in several places and projects all over Europe, the question is, of course, what protocol do you use to measure a quantum technology component, right? And of course, we can come up with a protocol, but it would be, and this is happening, of course, I think it makes total sense that this goes hand in hand with standardization, so that we have an agreed protocol that we use and understand how to measure things and also understand terminology. You know, what do we mean by whatever, a lifetime, a coherence, and certain properties. And I think this has to start now, and it does start, I would say. On your second question about international dimension, I would claim that in Sensenelec and also in others, we are connected strongly to international standardization bodies and try to synchronize, have a strong European voice that we have now after this work in the focus group, but also, of course, to align what we're doing in Europe with what's happening on international level. So maybe that's what I will say at this point. Thanks.
Thanks a lot, Nicolas.
So I can have I'm going to say complementary reply. So Nicolas has clearly and correctly focused on standardization. So that is also a part more that is service and support to society and industry. I would like to stress the research part, since Metrological Institute also are continuously active in improving primary standards and measurement protocols. So to reply, I think that we are very, very reactive to see the news in quantum technologies and to bring them into standards. So for example, okay, it's quite paradigmatic. I talk a lot about clocks, but the use of laser cooling for clocks is paradigmatic. Once laser cooling was proposed in the atomic physics community, metrologists started to think how to use them. And for example, another not well-known story is Bose-Einstein condensation, how to use that for clocks. So we have not been successful, so it's not a well-known story, but there are people that are really stressing the possibility to use this kind of this kind of physics for standards. And now, for example, introducing entanglement and squeezing is very important. The fact is that we are supporting standards, so we are not just very happy with the 1 dB improvements, so just an incremental improvements of the performance. We would like to have reliable and huge improvements, and this requires a lot. And when you introduce a novelty, then you need to ensure that the standards are reliable. If not, you cannot build all the chain of metrology. And this takes a lot of time, a lot of comparisons. It's not worth to state that you are at 10 to the minus 18, 19, 21, and so on. If you don't compare and you are not sure that you are not putting bugs in your realization. And this is the same, for example, with quantum communication or electronics. So we have not mentioned quantum sensing with single with Josephson junctions today. So, but every day we are pushing from the standards based on Josephson junctions towards something new and novelty. So who is working with quantum technologies in quantum metrology is really trying to make a difference and an innovation every day, looking at a bigger community.
Thank you very much, Davide. And I think on the hotspot, we can also directly answer a question of Philippe Rangier, who is saying that it was briefly mentioned that precision in comparing different clocks in different places is still better than the best clocks. Is that correct? Can you tell me more about how this is done and where are the limitations? I don't know if we prefer to answer it now or if you would prefer to write it, the answer, because you can also do this. And as this is a very interesting and a little technical question, but maybe the first part, like, is it correct? Just to confirm whether Philippe got it right.
Okay, so may I, on comparison, may I answer, since I know them quite well. So the precision in comparing different clocks in different places is still better than the best clocks. Okay, it is still better if you use optical fiber links in a very sophisticated way. If not, we are limited by the comparison techniques. If we use satellites, we are limited. So optical clocks are always better than satellites comparison. And if it comes to the fibers, it's not easy to compare global clocks with fibers, for example. So there is really also a constraint for the redefinition of the second, the so-called must-have, the criteria to propose a redefinition. One of the criteria is to compare distant clocks, remote clocks at 10 to the minus 18, well, 5, 10 to the minus 18. And this is not yet achieved. So it's not that easy to compare clocks. And if you go global and not just continental, like a European scale, things are still more complicated. This is why we have a lot of hopes in transportable clocks, just to move them towards the continents, across the continents, and have a comparison. But still, at the level that we need, this has not yet been done. And again, since we are metrologists, it's not just one experiment, one publication that fits what we have to do. It is a general reliability, a general result, and you can trust the quality of the metrology chain and the measurement chain. So I think that we are not at that moment, and also as responsible of one of the task force for the redefinition of the second concerned with the comparison, I have to say that we have to work a lot and to push all the colleagues to work a lot on this challenging goal.
Okay, thanks a lot, Davide, for this explicit answer. And now I would like to read a question from Martino Travagnin, and it is about the expected time to the market for the OptiClock.
Well, I can say a few things. Since we are a National Metrology Institute, obviously that's not our task, so I don't know the details. The only thing I can tell you is that the research project result is here at PTB, it's working, and one of the industry partners is actively working on creating an industry prototype out of this. So that's all I can say. So I don't know any more details than this, how long it will take. But I guess, I mean, you can basically see it was, of course, a major challenge, right? And this is very much connected to what Davide said. You know, setting up something for research is one thing, but then if you want it to work reliably, and even in this case have it, in a rack and transportable, it's much more effort.
Thanks a lot, Nicolas. This is very interesting. So as we do not have yet that much experience, it's difficult to predict. Won't even the most smart computer on earth trained by predict that. So Davide, do you have something to add to this?
To decide to market all the optic clock. Well, I think that it's again, I will not give an answer because it's not me to build up the industrial business plan of optic clock. But again, it's really a complicated also story of performances, reliability, and the market itself. So what are indeed the needs? What is the price that the market is ready to pay for such a lovely clock? And this is always coming to the discussion when you talk with companies. So a company will tell you that the best clock in their view is the quartz clock, because they can sell millions and millions quartz clocks, and they are very, very satisfied with this. But then when it comes also to commercial clocks that are already available, like hydrogen maser, and you make just the counting on how many hydrogen maser are sold by year, well, there are tens. And so this is a weird market, but without the hydrogen maser, you cannot have a global navigation system. So it's a very complex market. And even when it comes to reliability of the market, the point of failure of the supply chain are complex. So maybe it's all the same also for other business case. But here I can just comment on the clocks, since it's our a daily life experience also with the company. So no answer, but but in any case, they are pushing hard that.
Very nice. Thanks a lot. So we have a hand raised by Costanza. So probably she has something to say. Costanza, can you activate your microphone yourself? Yeah.
Can you hear me?
Yeah.
Yeah. So I mean, I find this answer very interesting in the sense that it brings to the impact of quantum metrology much beyond the impact through companies, through standardization. So apparently this is also very relevant for basic science. And if we want to push big adventures of humanity, like a man on the moon adventure or woman on the moon adventure, then we really need quantum metrology and the Euramet system. So this is one of the questions that I have, whether this is correct, whether this is indeed one of your goals. And the other question I had was how do we compare with respect to the efforts overseas on quantum metrology?
Well, I don't know, maybe I start, Oksana? Okay, so the first question was about fundamental research and metrology, and I can only enhance and stress what Davide also said. Of course, this goes hand in hand. I mean, I try to focus on services and industry a lot, but it's not by coincidence that the same people that work on fundamental science at PTB using clocks and INRIM, for instance, are the ones that are coming up with industry close to industry prototypes, because it is the same technology. And I agree that this also offers new opportunities, of course, in fundamental science, and something like a very good frequency reference, of course, can also, or good lasers. I think it's obvious for very good lasers can and need to be used for fundamental science, for sure. So I think this is definitely a connection that is very important, and also it makes sense to use this synergy. So it shouldn't be isolated, and it isn't, I would say. Yes, so my answer is yes, of course, Euramet, EM&Q, and all those collaborations are extremely important, and this connection to fundamental science should be carefully further developed, and it is, I would say. And the second question, I forgot. Oh, you said the international competition. Yeah, I showed a bit about this. You know, OptiClock is basically targeting at this hydrogen maser, and I showed the numbers. So it offers better performance in certain key parameters. And then, of course, the question is, where do you need it? But in the end, it's something that can be commercialized, that gives something that's better than the device you can buy on the market right now. And of course, then you need to figure out which applications you can use it for. But as far as I know, there's no other optical clock demonstrator that's that close to being an industry prototype. So the one I showed is the hydrogen maser, so that's a different beast. And then there are chip scale clocks, but they are not optical clocks with that high degree of relative frequency uncertainty. But it is a bit involved, so that's we would need to talk in more detail about this. So yes, there is competition, but I think in Europe there certainly are parts in metrology and fundamental science where Europe is competitive for sure.
Thanks very much, Nicolas. Thanks. So Davide would add something, I suppose, and then we will have one last question to answer before we will close.
Okay, so I think that we had to think about the chicken and egg situation where fundamental science and applied science are mixed together here. And of course, we all know that this is a false question. So we have to promote basic science and to interact with applied science. And but to have a statement also that is a positive one, I think that all the initiatives, starting with the Quantum Manifesto, the Quantum Flagship, is going in that direction. Because at the beginning, there was a push for scientists, for fundamental scientists to look at the impact and the role in society. And this scheme is even moved forward by the European Quantum Communication Infrastructure Initiative, where the challenge is offer services in 10 years, building on a quantum technology based on photons that is still mature in some aspects, but still fundamental science in others, like a lot of relevant achievements to be done in entanglement, for example, and entanglement distribution. So I think that this is very, very exciting, very important. The Commission is doing a lot of work on that. And this is the right roadmap, because if we want to be a knowledge-based society, then we cannot be just search for external suppliers across the world, but we have to produce our fundamental science, and we have to produce our fundamental technology for products. That comes to the question, what is happening overseas? Overseas, they are really pushing for new technologies, both on, I think, on the all 4 pillars. And you can have a look who is building or claiming to be in the situation to build a quantum computer, and who is building large infrastructures for quantum communication. I think that this is, as Nicolas said, always a bit of competition, but also something that you are not alone with your ideas that can be so crazy. These ideas are shared among the global community. This means that probably there will be more competition, and so a tough competition. But at the end of the day, we are not producing knowledge that are very, very good for our dreams, but not for a daily life. I think that these technologies, together with the new trends in medicine and the cited artificial intelligence, will change our society in the next 10 to 15 years. So this is just an indication of the time frame. I'm on the optimistic side, but I'm really convinced that in 10 years things will be quite different from today.
Thank you, Davide, for this very promising expectation and positivism. And let's profit that we still have a lot of people with us and answer the last question, which will be a little bit changing our perspective. But now I will kindly ask you to translate the quantum clocks into the qubit logic and to try answer how many qubits the clocks currently need. Or I was thinking how to adapt it better. Maybe what would be the minimum amount of qubits these clocks need, or maybe you have another alternative question.
Yeah, that's a well, I mean, it's very easy to answer. On one hand, it's maybe a little bit more involved. So OptiClock has exactly one ion at this point, so it's one qubit. But maybe to put this into perspective, I think it is a fair question, because the same control we have over qubits for quantum computing is the one we need for clocks. So it is indeed a qubit in the end that we need to control for a single ion clock. There are also other technologies like so-called lattice clocks that use 10,000 of atoms that are controlled in a certain way, maybe not as closely as a qubit, to be fair. However, I also would like to mention another technology that makes the connection between metrology and quantum computing and qubits and clocks even closer, and that is quantum logic spectroscopy. I mean, this is a way where you have one ion that gives you the reference and another one to read it out. And the two are interacting by the Coulomb interaction. And indeed, you can think of this interaction as a very simple quantum computing gate in some sense, right? And this really shows you this is a 2-qubit system for a clock that uses the ideas, the technologies, the concepts, even the algorithms of computing. And I think, again, this is along the lines of, you know, fundamental science, in this case, directly feeds into new generation of clocks, and in this way also to technology and metrology. So that would be my answer at this point.
It was easier than expected, at least by the person who put the question on. And Davide?
Well, I think that the reply was complete. Maybe I have to say that with the one single qubit, you can have already a wonderful optical clock, especially for 90% of the applications. And having more ions or having a lot of atoms is improving some technical aspects like the signal to noise ratio. And so, for example, can give you a faster measurement. And this is, for example, I think is very, very relevant to these 10,000 qubits that mentioned by Nicolas, to use the same language. Is very useful for fundamental science, for example, to obtain a very measurement on tiny effects in the shortest possible time. So I think that the need is indeed can be analyzed with respect to what you want to do. Mm-hmm. And so at the moment, I think that we have all the qubits, let's say the capability to manipulate atoms at the level that we want to do. Then probably the number of them, a bit more subtle quantum physics inside the clocks. I mentioned spin squeezing, for example, would be very relevant to improve at least a factor 10 the stability of the clock, and then will improve of a factor 100 the speed of the measurement. So this would be very, very nice, but I don't think that at the beginning of the clock or clocks like that will suffer from lack of number of qubits, let's say. That is the stability of the clock for society. So this is so we have all the qubits that we need at the moment, but who knows? We wait for the next Nobel Prize to leap forward.
Thank you very much, Davide. This was awesome. So I really like this logical speaking about metrology. I have to admit that I've never heard this before. And it seems like while for computing we have a problem of scaling up, for metrology, we needed to solve a scaling down problem, which was solved already by getting the control of a single qubit. But now, as Davide was mentioning, maybe retaking the street of scaling up, we can get error corrections and whatever functions that are extra needed for more involved and advanced metrology of the future. And let's leave it to the future science fiction movies for the moment. And on this really, really happy note, I'm looking forward for our next session that will be on communication in December, first week of December. And thank a lot to our speakers, Nicolas Spethmann from PTB in Braunschweig, Germany, and to Davide Calonico from INRIM in Italy. By the way, the city where Davide is, I have omitted. Davide, which city are you in currently?
In Torino.
In Torino, exactly. So Torino, Braunschweig, and Trieste are greeting everybody and looking forward to see you in the next session.
Thank you. Bye-bye.
Thank you very much. Bye-bye.